We've already covered the basics of modulation, but not the details. In this lesson video, I'm going to cover amplitude modulation, the simpler of the two. For modulation, you need two waves, which are the signal wave and the carrier wave. The signal wave is the one that has the information that you want to transmit. Maybe it's your voice, or a song, or the contents of a website. Whatever it is converted into a wave that could take any kind of random pattern. Or it could be a simple sine wave like this. That makes learning easier. Okay, so the carrier wave is generated to carry the signal wave. The carrier wave is a high frequency sine wave, at least double that of the highest frequency in the signal, with an amplitude at least double that of the signal wave. Then we kind of add the two waves together. When the signal wave is 0, the carrier wave is unaffected. When the carrier wave is positive, the signal wave is positive, the amplitude of the carrier wave is increased. And when the signal wave is negative, the amplitude of the carrier wave is decreased. So it's quite simple, really. The amplitude of the carrier wave is being modulated by the strength of the signal. Let's have another listen to what it sounds like. It's not just a simple mathematical addition though, and although we don't need to look into the maths of how modulation is actually done, we do need to understand a really important effect of the process. The act of modulating creates a new wave that has the same frequency as the carrier wave, but it also creates two new waves. These are called sidebands, and as you can see, they have frequencies of Fc plus Fs and Fc minus Fs. So Fc is the frequency of the carrier wave and Fs is the frequency of the signal wave. Most of the transmitted power is in the main frequency, but the two sidebands are significant. This causes a problem because instead of having a nice single frequency wave to transmit, the transmission now has a bandwidth. That's an important word to be able to define, by the way. Anyway, why is this a problem? Well, let's say this is my phone transmitting at frequency Fc. Your phone also needs to transmit, but if we use the same frequency, they're going to clash, aren't they? So the problem is now, even if your phone uses Fc minus Fm, we're still going to clash. You're going to have to move your carrier frequency all the way down here so we avoid one another. So these sideband frequencies mean the transmitted waves take up more space in the frequency range, so we can't fit so many phones in. Now this is one reason why we want to use very high frequency carrier waves. Modulating a 40 kHz carrier wave with a 20 kHz signal would pretty much take up all the space. But modulating a 40 GHz carrier wave with that same 20 kHz signal would hardly affect the bandwidth at all. It's all relative. For a real-world case, it looks a bit more complicated still. Because we are transmitting data, not just a sine wave, we get smeared out sidebands. Like this. Now, sticking with a voice signal, frequencies all over between 1 Hz and 15 kHz could be present. So we're going to get sidebands at each of these points. In the end, it looks a bit like this. I can put some numbers in. Let's say the carrier wave is exactly 1 MHz. So the upper sideband will stretch to 1.015 MHz and the lower sideband down to 0.985 MHz. The bandwidth is the range of frequencies that the transmitted wave occupies, which in this case is 30 kHz. So no matter what happens, the bandwidth will be 2 times the highest frequency present in the signal. By making the carrier wave frequency really high, we have made the bandwidth small relative to the actual frequency. Since we work with frequencies on a kind of log scale, this effectively makes the bandwidth smaller, so we can fit more transmissions in the total spectrum available. In other words, instead of having 10 transmissions with 30 kHz bandwidth fitting in a spectrum of 300 kHz, we can have 10,000 transmissions with 30 kHz bandwidth fitting in a spectrum of 300 MHz. And that's an introduction to amplitude modulation and sidebands. In the next lesson video, we're going to have a look at frequency modulation and see what advantages these two methods have got. But we're going to skip sidebands for frequency modulation because, quite frankly, it gets pretty complicated.